Hello everyone, welcome to another session in the machine learning series. Today we'll basically discuss ensembling method is called as boosting. So before this, we basically discuss in detail about decision trees. We discuss in detail about random forests. Today we'll actually spend time discussing what is boosting. Right? What basically whenever we talk about boosting, like what basically happens internally. Right. So the basic idea over here also remains the same. Right. How do you combine multiple learners? Right. How do you combine multiple learners so that one, your accuracy is improved, your model performs well at the same time making sure that overfitting reduces, your variance reduces. Right? This is we discussed random faults in the previous session. Right? In this session, we basically discussed boosting. Uh, so the main idea of boosting is sort of whatever errors you make in the first iteration, right? You sort of make improvements to that. The model sort of learns from whatever errors you make. So that is sort of the fundamental idea of boosting. Right? But say when you actually compare that with your random forest, right? Random forest basically say once you generate your bootstrap samples and you give it and basically on each bootstrap sample you get basically each different tree. Actually, those are sort of parallel learners. Say one tree is not dependent on the other tree, right? Because each of them are taking a separate data set, then they would have its own constraints in the number of columns it can choose, right? But boosting is not like that. Boosting is sort of a sequential process, right? So it's like once you build a tree, then again there's another set of tree which is built. So it's sort of a sequential process, not a parallel process, say, similar to random forest where one decision tree is independent of the other. Right? So this is what boosting is. So obviously the first boosting framework was actually first boosting algorithm was something called the ADA boost. But nowadays, then obviously there is something called the gradient boosting message, which was actually very popular. Obviously mainly because it was performing very well and also it was very robust. Further, I think nowadays one algorithm called extreme gradient boosting or XGBoost. Then there's light GBM. There's again a whole lot of different boosting algorithms which are actually quite popular. They're not popular not obviously because of the names, but also because they perform very well on tabular data. So we'll basically look at let's go step by step to see how actually a boosting algorithm work. Right? The first step is obviously we are using decision trees as a base. So we are just basically combining multiple decision trees. Right. So yeah, what we're doing is we're just combining multiple decision trees. So the first step for the first obvious step would be to just fit a decision tree to your data. Right? So this is the first obvious step. The first obvious step is basically fit a decision tree to your data. Right, fit a decision tree. Fit a decision tree to data. So this is the first obvious step. After you put a decision tree to your data, the next step basically is you calculate your error residuals. Okay. Now, what do I mean by error residuals is it's nothing but the difference between actual and predicted. So assume if this is your predicted, you're just making it as y underscore predicted one. So your error residuals is nothing but y minus, say assume e1, if e1 is your error residuals, it's y minus y underscore predicted one, y underscore predicted one. Right, so first you calculate error residuals. So this is where I think you just maybe need to just understand a bit. It's in third step. Basically, what you do is you fit a new model. That's understandable, right? You fit a new model, but you fit a new model on what? You fit a new model using your error residuals, right? You fit a new model using error residuals as your target variable, right? You fit a new model using error residuals as a target variable. From this, you obviously get your predictions as well, e1 underscore predicted. Right. So, and again, so now basically what you do is you basically add this prediction which you get back to your original y pred. Right. So you basically get something which is called as y underscore predicted 2. It's y underscore predicted 1 as e1 underscore. Right. So this is what actually happens. So this is like say these 4 steps are one cycle. Then again the whole thing again repeats. Again you will calculate your error residuals, y minus y underscore score predicted 2, you calculate error residuals. Again, you fit a new model using the E2 as a target variable, you get predictions. Again, you create y underscore predicted 3, right? So you get the y underscore predicted 3, and the process again repeats. Right? So this is what the boosting algorithm is. Obviously, this is sort of at a very basic level. There will be again a whole lot of parameters, whole lot of additional complexities added, but basically this is what is boosting algorithm. So next time, I think whenever maybe you're asked to say what is boosting algorithm, what actually happens in the boosting algorithm, I think this explanation would be, but maybe if you want in detail how to know how XGBoost works or GBM works, but this is the basic idea. I think on top of this, you would obviously be adding a bit more additional complexities over there. One of the major differences between GBM and XGBoost is in terms of regularization. So in XGBoost, you basically have something which is called as regularization is already implemented in the tree building process. In GBM, it's not there. I think we had a discussion on regularization during the discussion on bias variance trade-off, correct? Where we basically saw for the issues of overfitting and underfitting, one possible solution was to use the regularization, either use the L1 loss or L2 loss. Then the other difference basically is parallel processing. In XGBoost, the tree building process or the sequential model building process is parallel. It has been written in parallel code. Not the case with GBM. And XGBoost actually has a built-in routine to handle missing values. Right, so it has a built-in method to handle missing values. And also, there's one more difference being tree pruning. So what would GBM do is so whenever sort of enters a negative loss, right, it would immediately stop the tree building process. But XGBoost is not that. So XGBoost is more of a say it prunes the tree. GBM is more of a greedy algorithm. Right? So it splits. So it basically what happens in XGBoost is it starts the tree building process. It splits up to max depth. After that, it starts pruning the tree. Right. Yeah, I think these are the major differences, and also in terms of programming, right? I think the major difference in XGBoost and compared to GBM is more how it is internally written, right? Algorithmically, there's not much of difference. So even while calculating the splits, what happens in XGBoost is it sort of approximates the splits through histogram. So whatever splits it calculates, sort of approximates it. So not the case in GBM, right? And so the major reason for improvement in performance, at least runtime performance in XGBoost, is because it's a lot of good programming practices actually been put into it. One, it's parallel. It supports parallel processing. Then it actually runs on sparse matrices. And data structures are actually way improved. The processing data structures in XGBoost are actually way improved. So mainly because of these many reasons, XGBoost is actually very, in terms of performance, it's actually very fast in comparison to GBM, and also in terms of runtime, also in terms of performance. Okay. Now, basically, XGBoost has a whole lot of different parameters. So basically, what we'll do is we'll try to understand what are the different parameters in XGBoost, and after you understand that, maybe we'll look at different ways of tuning your parameters, right? So again, we had a brief discussion on this where we saw one is you can do for tuning of hyperparameters, one you can do a random search, one you can do a grid search, or if both of them does not give you good results, you can basically try something called as hyperparameter optimization, Bayesian hyperparameter optimization. Okay, so we look at XGBoost parameters. What basically XGBoost parameters? There are basically three different types of parameters. One is something called as general parameters. Other one is booster parameters. Right. So general parameters basically are your what type of booster do you want? Are you trying to get tree-based booster or a linear booster? Right. And the number of threads, as in, do you want the program? Do you want the code to be run parallel, multiple threads, like 2 threads, 3 threads? You can specify it. Then the number of features. So by default, it's automatically set to all, but most of the time I think it's not. Different options are not right, but this definitely is a feature, right? Then you can see eta is a learning rate, gamma is a minimum split loss. Minimum split loss. I think this is that example which is alright. So suppose you have a data set with 100,000 rows, and you have in one node you have only 10 rows, 10 data points. Obviously, you can't continue with that. Right? Basically, if you put 10 as stopping condition, obviously you can't continue. And also deciding on 10 as a stoppage condition is also one of one of parameters so which will basically calculate that number for you. Right. Also would have calculated using any optimization algorithm. That is also fine. This is max delta, step, subset. So you mainly use ones are max depth, gamma, eta, then subsample. So either you can get a subsample for everything, or you can either subsample by tree, or subsample by row, or subsample by column. All of that is possible. Lambda is basically your regularization term. L2 regularization, alpha is your L1 regularization. And what type of tree building process you build? Either you build approximate splits, or do you use histogram to calculate the splits? All of that. It can, so XGBoost supports GPU processing as well. That is also here. So the next is linear booster. So if you choose your boosting algorithm as linear, so these are the different parameters which are available. So 2D is mainly, 2D distribution is mainly used for sort of insurance-based applications like count data. So whenever I think you get more count data, then 2D is generally preferred. So this is your learning task parameters. So whether it basically supports, say, you're running a binary classification, multi-class classification, or you're just running a sort of a regression. Then if you're running some sort of survival analysis, or you're running any Poisson distributions, so it basically has the support for everything. And then it has support for eval metrics as well. So obviously you can code your own eval metrics, but XGBoost offers support for certain specific eval metrics, root mean square error, then mean absolute error. It has basically support for each one of these error metrics. Right. So yeah. So this is what the different parameters for XGBoost. Obviously, I think XGBoost, maybe once you practice on how do you actually call XGBoost and how do you actually implement XGBoost, then maybe I think you get a better understanding on the actual working of the model. Okay, guys, and thank you. I think the next session will again meet where we'll basically discuss the other topics in machine learning series. Thank you.